just going to flash some of these examples here. This is behavior from several different types of neurons. Some of these neurons started changing their activity several seconds before. I don't think that these are spontaneous fluctuations, as well they were referred to as earlier. These are changes in the activity of individual neurons. This is not average noise at the level of scalp EEG signals. Not only did some neurons increase their frame rate, other neurons showed a decrease in their frame rate. And there are a lot of technical questions that I'm going to skip in the interest of time. The examples that I showed you, the individual neurons, are also reproducible at the level of populations of neurons. We observe this in terms of multi-units, in terms of single units. We observe this in the 4 different locations that we studied in the frontal lobe, and not in other locations in the medial temporal lobe. The results were robust to different ways of defining the baseline. There has been lots and lots of discussions about how to define the baseline in the limit type of task. Essentially, it doesn't matter here. If you artificially jitter W, I always felt that people were very imprecise in how they report W. There were some discussions earlier about whether W really matters or not. And we think that W does matter in the sense that if we jitter W, we would have gotten different results, at least for jitter amounts in the order of 100 milliseconds or so. We spent more time than I care to admit trying to study whether individual neurons in single trials show gradual changes or abrupt changes. And that's a very hard question, and I don't think I have a clear answer on that. I'm happy to discuss that further if anybody's interested. I'm going to skip some of the details of how we use machine learning techniques to decode and make predictions in single trials. This is now pretty standard in neuroscience. We take spikes from this set of neurons, we count the number of spikes, we feed those into a classifier. For the aficionados, we use a support vector machine with a linear kernel, and based on this, we can ask whether we can actually make predictions about when people will or will not make a decision from the activity of a set of individual neurons. And we can actually get relatively accurate in the sense that we can predict when people will make a decision within a couple of 100 milliseconds from the activity of a pseudo-population of a couple of 100 neurons. We implemented one possible biophysical mechanism by which this could happen, which has to do with projecting the input from a lot of these neurons to a very simple integrate and fire mechanism that would integrate information from many of these neurons and actually execute these when the threshold is crossed. This is similar to the threshold idea that was presented in one of the earlier talks today. We don't have really any evidence that this is the real mechanism by which neurons actually implement decision, but this is a potentially very, very simple way in which this could happen. We also did some work trying to ask whether we can predict not only when people will make a decision, but also what type of decision subjects will do, and we've been somewhat successful in that as well. So I'd like to simply summarize this second part of the talk by arguing that neuronal activity in the frontal lobe precedes volition. Again, this is at the level of individual neurons. I made already a lot of technical points that I'm going to skip now. There are, of course, lots of caveats. I'm going to skip most of these. You are also, of course, very familiar. I'm not trying to argue that we can record the activity of neurons and make predictions about what you're going to have for lunch tomorrow. This is only on a scale of a couple of seconds. This is, in a sense, we're very, very limited in terms of what kind of predictions we can do. So just to drive home the notion of no randomness, I want to make the case that in the case of strong determinism, as it doesn't escape the attention of any of you, that strong determinism means that absolutely everything should be predictable since the start of the universe all the way until now. That's a very, very strong version of determinism. I'm not willing to defend that, but I am very willing to defend that next year, in 2018, Argentina will win the World Cup. I'm sorry for the Germans. Finally, I actually didn't do any of this work. The people who are actually really important are Itzhak Fried, a phenomenal neurosurgeon who implants selectors in these patients, and thanks to him we were able to do all of these recordings, as well as Rick Bourne, who did all of the recordings in macaque monkeys. So I'm going to stop here. I'll put this again just in case.
We are talking about the World Cup later.
All right.
Okay. The questions to the randomness. That's randomly picked out.
What is the variability in terms of predicting W as opposed to predicting the actual movement?
It's almost identical. W and P are strongly correlated on a trial-by-trial basis, and we could have written the entire paper based on predicting P, and we would have gotten exactly the same results. So at least in our hands in this experiment, W is strongly locked to P. Essentially, people don't make a decision and wait 2 seconds until they execute the movement. So basically, they're
very, very strongly correlated.
They're very, very strongly correlated. We actually redid the entire paper based on P, and we got exactly the same results. It's just sexier to write different about W, and that's what we did. But it's identical.
Okay.
Yeah. A couple of points. So one is, I mean, you mentioned that these are neural recordings, right? And this is the gold standard. And this is somehow different in terms of the stochastic explanation from EEG recordings. But I don't think it matters, right? That explanation holds no matter how you record. It doesn't matter how you record the activity. If there are intrinsic fluctuations, and there are at the level of single neurons, and the initiation of movement tends to coincide with crests in those fluctuations, then you'll recover something not only in the average, but on single trials as well. It doesn't really matter.
I don't know any evidence that suggests that there's any randomness in the activity of these neurons. I think that's what I was trying to say.
Yes. There are fluctuations.
Deterministic fluctuations. Yes, absolutely.
Okay.
Yes.
Okay. No? Okay.
I mean, so my postdocs are on Sigtuna to really sympathize. But with regard to the first half, with regard to the use of randomness, it seems to be wanting to restrict that to the use of the term randomness, a very, very strict set of events. And that reminds me sort of a discussion that has been ongoing, and I hope settled by now, I can check, for a long time in evolutionary biology, when people would say that, oh, no, mutations are never random. Because, I mean, I look at this one mutation, single base pair change. I know it was a UV ray that hit that base pair and changed it into a different one, so that's totally not random. And, on one level of explanation, that's correct. But of course, I mean, where the damn thing hits the DNA strand is pretty much random. Unless, you go and say, well, but it's not random because the ray came from the sun and it had to go precisely that direction it did right there. With regard to the information, so to say.
For a lot of practical purposes, I'm happy to use the word random for a lot of practical purposes. So we were discussing this a little bit over breakfast. I don't see any randomness in flipping a coin. We can actually use the word random. You can flip a coin to see who will play on which side in soccer, because it's pretty. But strictly speaking, I'm using the word randomness to imply quantum mechanics, and everything that's not quantum mechanics is not random according to this definition. That I think is true randomness, and everything else we can call it randomness, but ultimately there's a very simple mechanistic, deterministic explanation. Maybe chaotic, maybe strictly dependent on initial conditions. All sorts of for our eyes it may be random, but it's not true randomness in the quantum mechanics sense. That's the.
Okay.
How do you rule out that the W moment is the moment that you decide to make a movie?
That is not. I don't know. We did exactly Leavitt's experiment. We didn't innovate at all in there. So we asked people to report when they make movement. They report this time. We call it W. I don't know. We can debate about what exactly that means. There was a talk earlier today that was very interesting. It argued that the W is particularly relevant. This is an operational definition, exactly in the Leavitt sense. Nothing. We can debate about what that really means for subjects.
Okay, one more.
Even if we agree that there are no other quantum domain effects generating randomness in the brain, we have to grant that there's Brownian motion in the synaptic clefts, in the diffusion of neurotransmitters across that gap. And in order to minimize the variability of arrival times of a neurotransmitter, you want to minimize that cleft difference. But the cleft is actually reasonably big. It's not 1 nanometer, it's 20, 30, 40, 50 nanometers. So why do you think evolution would come up with this big gap that would lead to variability in arrival times of neurotransmitters, which will lead to variability in depolarization, BPSPs, which will lead to variability in spike timing?
I think it's a fascinating question, and again, I think there may be a lot of useful, evolutionary useful reasons why you may want to have apparent variability. Unfortunately, I missed Bjorn's beautiful talk, but he was trying to show some of it to me. The question of the zebra, trying to be random in one way or the other. We can talk about spike timing versus rate codes, and I think those are, but strictly speaking, I refer to Brownian motion as not a random effect, as long as it's not quantum. But we can discuss about why, and there may be a lot of evolutionary advantages why you may actually want to have some amount of jitter in spike timing, why you may want to have behaviors that are not perfectly predictable. I'm not against any of that. I'm just, the main distinction I'm drawing is between quantum and not. And we may disagree.
Okay, I see. There is no randomness. Is everything already determined?
I knew you wanted to say that, yes.
Yeah. Also that Argentina is
And if anybody wants to bet about this, I'm happy to.
there is some rules, so sometimes Argentina is winning, sometimes
That's going to change over the next couple of decades. But yes.
Okay, good. So now we are, let's think again.